integration and trig substitution. Now, trig substitution is used when we have something like this in the form of this, or this, or this in the integrand. So we either have a squared minus x squared, square root of a squared plus x squared in the integrand, or x squared minus a squared in the integrand. Now, when we have a squared minus x squared, by recognition, if we want to do this from memory, this is x equals a sine theta, and this one x equals a tan theta when we're doing the substitution, and in this one x equals sec x equals a sec theta. Now, why do we choose sine, tan and secant? We choose these because we can use the identities. So for sine we use the identity 1 minus sine squared theta equals cos squared theta. For tangent we use the identity 1 plus tan squared theta equals sec squared theta, and for secant we use secant squared theta minus 1 equals tan squared theta. So these identities are linked with this particular trig substitution, this one with this trig substitution, and this one with this trig substitution. Now, say we're in an exam situation and we didn't remember which trig substitution to use. So how do we get this particular substitution? Well, it all comes from Pythagoras. A squared plus b squared equals c squared, and some bright spark thought, hey, this formula looks like this, so maybe we can apply trig to it and then use this as a trig substitution, and then later on convert it back after we've differentiated, integrated rather. So Pythagoras used a triangle, a right angle triangle. So let's draw a right angle triangle for each of these. So in this case, a squared minus x squared, the a is the largest number, so that would equal the hypotenuse. And then we have to decide which one is the square root and which one is the x. And how we decide this is by using x over a is one of these. So we have the sine, the secant and tangent, and for the sine we know it's opposite over hypotenuse, secant is hypotenuse over adjacent, and for tangent it's opposite over adjacent. So in this case we've got a is the hypotenuse and we want x over a to equal one of these. So where x equals a, we have the sign, so that'll be the opposite over the hypotenuse. So this is a, h is a, and o would be the opposite. So in this case x would be the opposite, and this side over here would be square root of a squared minus x squared. This is theta and a right angle. So in this case, a squared plus x squared, from our Pythagoras formula, a squared plus b squared equals c squared. A squared, the square root of a squared plus x squared is the actual hypotenuse. So that'll be a squared plus x squared. Now we have to figure out which side is the x and which side is the a. Again, we use x over a is one of these. So where do we put the x and where do we put the a? If we have opposite over adjacent, that will equal tangent. So the x would be the opposite and a would be the adjacent side to theta, and that would give us tan. Okay. In this case, looking at the equation x squared minus a squared, the hypotenuse would be x, being the larger, minus the smaller a. So this would be x, this would be theta. So we have to now figure out which side would be the a and which would be the square root x squared minus a squared. So if we have a look at x over a, we know x is the hypotenuse, so it's going to be secant over a. So the adjacent is going to be little a, and the adjacent one is here, so that's a. And this one is the square root value over here, x squared minus a squared. These are called our reference triangles, which we have to draw in trig substitution when we want to convert back into our x values from our theta values. So this is how we work them out if we don't remember the formulas. Let's start off with a simple trig substitution. So if we have the integral of square root of 1 plus x squared dx. So looking at the integral, it looks like we can do trig substitution on it because it's a squared plus x squared. Now the thing to do now is draw our reference triangle to see which one of our tan, sec or sine substitutions we're going to use. We'll draw our right angle triangle. From here we can see that this looks like a squared plus b squared equals c squared, so this is going to be the square root value is going to be the hypotenuse, so this is square root of 1 plus x squared. Now we need to know which side is going to be the x and which is going to be the a. So we use x over a equals one of these. So tan is opposite over adjacent, secant is hypotenuse over adjacent, and sine is opposite over hypotenuse. So looking at this, to get x over a, we would have to use tangent, which is opposite over adjacent. Those are the ones we've got left, because the hypotenuse is already taken. So in this case, we're going to use a tan substitution. The x over a, so the opposite is going to be x, and the adjacent is going to be the 1 squared, or 1. And that's our substitution in the triangle. Now what we tend to do is write out that tan theta equals, and the adjacent was 1, so for x equals tan theta, and then dx equals when we differentiate tan theta, we get sec squared theta d theta. So when we substitute, we get 1 plus x squared becomes tan squared theta, and we'll dx, we're going to substitute dx with sec squared theta, so this becomes 1 plus, sorry, that should be under root, tan squared theta. The dx becomes sec squared d theta. This is the identity sec squared theta. 1 plus tan squared theta equals sec squared theta. So this becomes sec squared theta, sec squared d theta. When we take the square root of sec squared theta, we get sec theta, so that becomes that, times sec squared d theta. When we combine these two, we get the integral of sec to the power 3 theta d theta. Now when we integrate sec to the power 3 d theta, we get a half sec theta tan theta plus a half natural log sec theta plus tan theta. So when we do that, we get a half. So sec theta from our reference triangle is square root of 1 plus x squared times x, and this would be, sorry, sec theta, tan theta would be that, and that would be plus the natural log of sec theta plus tan theta, which would be 1 plus x squared plus c. Just an aside on this transformation, let's just do a bubble. So sec theta equals h over a, which is the square root of 1 plus x squared over 1, and tan theta equals opposite over adjacent, which equals x over 1. And that's where we get these values from. Integral of dx over square root of 9 minus x squared. So let's draw our reference triangle first. That's theta. So we know that 9 is the bigger number, that's going to be the hypotenuse. So that's 3 squared is 9, so the hypotenuse is 3. Now we have to decide which is the square root value and which is the value of x on the triangle. We get this by using x over a, and we use sine, tan and secant. Sine is opposite over hypotenuse, tan is hypotenuse over adjacent, and tan is opposite over hypotenuse, and secant is hypotenuse over adjacent. Right, now that we've done that, we want 3 is a, so that's a, because it's a squared minus x squared. So a on the bottom as the hypotenuse. It can be either sine or tangent. We don't know it's not tangent because tangent is always a squared plus x squared. So it's, in this case, it's sine that we're going to use. Sine is opposite over hypotenuse, so the x will be the opposite. The a is the hypotenuse, so the adjacent then must be the square root value, which is 9 minus x squared. Right, now that we've got that sorted, let's write out that we're using the sine value. Sine theta equals x, the a is 3, so x equals 3 sine theta. Now dx is 3 cos theta d theta. Sometimes if we want to find the value of just theta from sine theta equals x over 3, if we just want theta by itself, theta is sine to the minus 1, or arc sine x over 3. Now that we've got those values, we can do the substitution. So for dx we've got 3 cos theta d theta, so this becomes 3 cos theta d theta all over, square root remains, 9 minus, and then the x squared becomes 9 sine squared theta. Now we can use our, let's put this down first, so that's 3 cos theta d theta. If we take our 9 out, this becomes 9, 1 minus sine squared theta, so that's factoring the 9 out. This identity we know as cos squared theta, so this becomes the integral of 3 cos d theta. Square root of 9 is 3, and the square root of cos square theta is cos theta. So here we use the identity 1 minus sine squared theta equals cos squared theta. And then we took the square root of it to get 3 cos theta. So this, when we cancel the 2, the integral of d theta. And we said the theta was arc sine x to the x over 3. So this becomes when we integrate d theta, we get theta plus c, and this theta is arc sine x over 3 plus c. Integral of square root 25 minus 16x squared x dx. Let's draw a triangle. Sine, tan, secant, opposite over hypotenuse, opposite over adjacent, and adjacent over hypotenuse. That should be hypotenuse over adjacent, sorry. Cos, so it's the inverse of cos. Now on our triangle, we know that the 25 as the larger value will be the hypotenuse, so the square root of 25, which is 5 squared, will be 5, and that equals a. Now we need to figure out which one will be the square root value, which side, and which side will be the x value. So we use x over a. It is going to be one of these, and when we look at that, we see that it's the opposite over the hypotenuse. So the a is the hypotenuse, which is on the bottom. So we're going to use sine substitution. So this is the 16x squared, or 4x, and this leg here of the triangle will be 25 minus 16x squared. Sine theta, because you know we're going to use sine theta now, is 4x, which we've figured out there, over 5, which is the a. So taking the 4 to the other side, we get x equals 5 over 4 sine theta, and then dx equals 5 over 4 cos theta d theta. Another value we can look at in this case is cos. Now that we've got the triangle, so cos is adjacent over hypotenuse, and the adjacent side is the square root value, so that's 25 minus 16x squared, and the hypotenuse is 5. So that's another little aside we can consider. If we rearrange this, we get square root, or therefore the square root of 25 minus 16x squared is 5 cos theta. And that's another little aside that we can use in our substitution. So let's have a look. We've got 25 minus 16x squared, and we just said that was 5 cos theta. So this will become the integral of 5 cos theta. And we said x was 5 over 4 sine theta. And dx. So now we want to replace the dx. So this then becomes 5 cos theta over 5 over 4 sine theta. Dx we said was 5 over 4 cos theta d theta. So when we rearrange this and do our division, get rid of this 5 over 4, this becomes 5 cos theta divided by 1, all divided by 5 over 4 sine theta. We can take the 4 to the top. This equals the integral of 4 times 5 cos theta over 5 sine theta multiplied by 5 over 4 cos theta d theta. We can get rid of the 4's there, cross those out and cancel out the 5's, and this equals the integral of 5 cos times cos squared theta d theta all over sine theta. Take the 5 to the outside of the integral. We get cos squared theta, using the identity, is 1 minus sine squared theta over sine theta d theta. So we're using the identity cos squared theta equals 1 minus sine squared theta. Substituting it in there for cos squared theta. We have one term on the bottom and 1 minus sine squared theta on the top. We can split that into 2, so we have 5 integral of 1 over sine theta minus sine squared theta over sine theta d theta. This is then the integral of 5 integral of 1 over sine theta cosec theta, and one of the sines crosses off with that sine, and we're left with sine theta d theta. And this, now we can integrate, and we get 5 minus the natural log cosec theta plus cot theta minus, and the integral of sine is minus cos theta plus c. Then all we do is use our reference triangle to convert cosec, cot and cos back to the x values. Integral of dx over x squared plus 9 to the power 3 over 2. We can use trig substitution because we can see that this 3 over 2, the 2 on the bottom, signifies that it's a square root. So the square root of x squared plus 3 squared. So let's draw our triangle, our reference triangle. This is going to be our hypotenuse. So that'll be square root of x squared plus 9. Now we need to work out our, whether it's sine substitution, a tan or a secant. Sine is opposite over hypotenuse. Tan is opposite over adjacent. Secant is the hypotenuse over adjacent. And we work x over a has to equal one of these. So we want to work out which is x and which is a, and a equals 3. If we look at them in turn, the opposite over the adjacent is the only one that fits to make tan. So the opposite will be the x, and the adjacent will be the a, which is 3 squared, which is 3. Tan theta equals, from there, x over a, which is 3. So x equals 3 tan theta. Dx is 3 sec squared theta t theta. So now let's do our substitution. So the dx goes over here as on the top as 3 sec squared d theta all over x squared plus 9 to the power 3 over 2. Let's have a look at the x squared plus 9. The x squared plus 9 becomes, x is 3 tan theta, so that's 9 tan squared theta plus 9, and then when we factor the 9 out, it becomes 9 1 plus tan squared theta to the 3 over 2. This then is our identity that we can use, which is sec squared theta. So replacing 1 tan squared theta with our identity, we get 9 sec squared theta to the power 3 over 2. Sorry, that should be brackets there. Okay, now this is 9 to the power 3 over 2 sec square theta 3 over 2, which becomes 9 to the 3 over 2, 3 square root of 9 is 3, then to the power 3 becomes 27, and sec square 3 to the square root of sec squared is sec to the power 3 becomes sec to the power 3 theta. So this then becomes integral of 3 sec squared d theta all over 27 sec 3 theta. When we cancel out, it becomes 1 over 9 integral of, cancel 3 over the 2 over there, we're left with just 1 sec here. So this becomes d theta over sec theta, which is 1/9 1 over sec theta, it's cos theta, the inverse d theta, and then when we integrate now we get 1 over 9, integrating cos theta we get sin theta plus c. Now we replace the sin theta from our table at the top, and sin theta is opposite over hypotenuse, so our final answer is 1/9, opposite is x, and the hypotenuse was square root of x squared plus 9 and plus c. And that is our answer. Take care sometimes, if we're faced with the integral of x over square root of 9 minus x squared, first of all try u substitution, and you'll get u equals 9 minus x squared and du equals minus 2x, and the x appears in the integral, so you can do that by u substitution. The integral would be minus a half u to the minus a half du, which is easier than doing trig substitution. However, if you were faced with the integral 1 over 9 minus x squared, you would need to use trig substitution. Integration of 1 over x squared square root of 4 plus x squared dx. First of all, let's draw our triangle. We know, looking at this 4 plus x squared, that looks like a squared plus b squared equals c squared. So this is the hypotenuse. Now let's look at where we're going to put the x and the a on the legs of the triangle. So we have sec is h over a, tan is opposite over adjacent, and sine is so O over h. And we want x over a to equal one of these. So we know that the a is 2, so that's going to be on the bottom and the opposite there, so this is going to be a, and it's 2 squared equals 4, so a equals 2, and our other side is then going to be x. So we're going to use the tan substitution. So tan theta equals x over 2, x equals 2 tan theta, and dx equals 2. Differentiating tan, we get sec squared theta d theta. So now we're ready to do our substitution. So on the bottom, let's do the bottom first, we have the integral of x squared, which is 4 tan squared theta, square root of 4, and then x squared is 4 tan squared theta again, and on the top we have dx, which is 2 sec squared theta d theta. Rearranging, we have 2 sec squared theta. Here we're going to use our identity. So this is moving the 4 out, we get 4 plus 1 tan squared theta, square root of. Then when we take the square root of that, we get 2 sec squared theta over 4 tan squared theta, and then 1 plus tan squared theta, the identity is sec squared theta, the square root of 4 is 2, and the square root of sec squared theta is sec theta. D theta. Okay, now let's see if we can do some cancelling. Well, that 2 cancels with that 2, and one of those secs cancels that, so we're left with 1 over 4. Move that to the outside. This sec theta on the top, and on the bottom we have tan squared theta d theta. Now whenever we have a tan squared, let's try and convert that into sines and cosines. So this then becomes a quarter. The sec is 1 over cos theta, and then the tan theta is, tan squared theta rather, is, tan is sine over cos, so tan squared is sine squared theta over cos squared theta d theta. When we flip the bottom fraction and bring it to the top, this becomes a quarter integral of 1 cos theta cos square theta, sine square theta, d theta. One of these will cancel with one of these, leaving cos theta on the top. So this then becomes cos theta over sine square theta. Now we can move this a little bit higher. We can bring the sine theta to the top, so that becomes a quarter. So that becomes that. A quarter integral of cos theta, bring the sine 2 theta, sine square theta to the top, that becomes sine theta to the minus 2 d theta. Here we can do u substitution, so we let our u equals sine theta, du then is cos theta d theta. When we do this, let's go this way, we get a quarter u to the minus 2 du, and when we now differentiate, integrate, we get a quarter u to the minus 1 over minus 1 plus c. Rearranging that, it's a minus a quarter minus a quarter u to the minus 1 plus c. Now what we have to do, once we've got this in the u form, convert it back into x's. So first of all we convert it back into sines and then into x's. So from this u substitution, replacing the u, we get minus 1 for sine theta plus c, and then using our triangle here to replace the sine theta with the x, we get, let's do a little aside, we get sine theta equals opposite over hypotenuse, which is x over the square root of 4 plus x squared. So now we're going to replace this sine theta with this, and the final answer we get is minus 1 over 4 square root 4 plus x squared plus c. And that is our final answer. And that is our answer. At the end of integration by trig substitution, we have to convert back to x's, so we have to integrate usually a secant, a tangent, a sine squared. Let's go over some of the common ones that we need to integrate. So for instance, the integral of tan x dx. If we make this into cosines and sines, this is sin x over cos x dx. Now wherever we see, if we want to do u substitution, we put u equals cos x, and then du will equal minus sin x. And if we see the sin x appear in the original integrand, the du appears, that means it's a candidate for u substitution. The constant, or the minus sign, we can take care of. So this would then, in our u substitution, would become the integral of minus 1 over u, and sin x dx becomes du, and when we integrate this, this becomes minus the natural log of u plus c, and when we replace the u with the cos x, this becomes minus natural log cos x plus c. So that is our answer. The integral of tan x is minus natural log cos x plus c. Let's have a look at the integral of sine squared of x dx. From our double angle formulas, sine squared x becomes the integral of 1 minus cos 2x over 2 dx, which is the integral of a half 1 minus cos 2x dx. We can split this into two integrals, distribute the half, so this will become the integral of a half minus a half the integral of cos 2x dx. So when we do the integration, this becomes a half x minus a quarter, and by u substitution this becomes minus a quarter sin x plus c. In our u sub of this, we let u equal 2x, and our du becomes 2 dx. In integration by trig substitution, right at the end, we're going to integrate a trig function. So let's have a look at some common sec or secant functions. So if we have the integral of secant x dx, what we can do is a little trick. We multiply secant x by 1 essentially, and how we do this is by multiplying it by sec x plus tan x. all over sec x plus tan x dx. So essentially this is 1 that we're multiplying by, and the integral remains the same. Now what we do is we distribute the secant x, and we get the integral of secant squared x plus secant x tan x all over secant x plus tan x. This is really good because what we can do now is a u substitution. So if we let u equal secant x plus tan x, du then becomes, the secant becomes secant x tan x, and then when we differentiate tan x, we get secant squared x, and as we can see this is the same as the top line, so this then becomes the integral of du over u, which is the integral of 1 over u, and when we do that, that's the natural log of u plus c. And then when we replace the u with our secant x plus tan x, we get the natural log of secant x plus tan x plus c. And that is the integral of secant x. Integral of secant squared theta d theta. This is really easy when we think about it. If we let u equal tan theta, then du is secant squared theta. So this becomes the integral of du, and when we do that, that's u plus c. So that's tan theta plus c. So the integral of secant squared theta is nothing but tan theta plus c. Integration of secant cubed theta d theta. We do this by integration by parts. Using the formula u dv equals uv minus integral of v du. This is then secant theta secant squared theta. So we let this equal our u and this equal our dv. So u equals secant theta du equals secant theta tan theta d theta. Our dv is secant squared theta, and when we integrate that, our v is tan theta. So now we just substitute back into our formula. So we get secant theta tan theta, that's our uv, minus secant theta, and our tan squared theta becomes secant squared theta minus 1 d theta. So the integral of secant theta d theta equals sec theta tan theta minus the integral of secant of theta d theta plus the integral of secant theta d theta. When we multiply out, when we distribute the secant theta, that's what we get. We also have to distribute our minus sign, and that changes this to a plus. Now we have secant to the power 3 theta here and secant to the power 3 theta, so it looks like we've gone in a circle, but what we do is we bring this to the other side, and the minus becomes a plus, so this becomes 2 secant cube theta d theta equals sec theta tan theta plus, when we differentiate secant theta we get the natural log of secant theta plus tan theta plus c. And now to get our what we wanted, which was the integral of secant cube theta d theta, we divide through by a half to get rid of the 2, so this becomes a half secant theta tan theta plus a half natural log of secant theta plus tan theta plus c. We really should half the c, but it still remains a constant. So c over 2 is still a constant, so it remains a c.